Hello everyone. In this video lecture we are going through an example of drawing a Root-Locus plot for a given system. As you can see over here, the GP of S, the transfer function of the system, is given as 16 over S times S plus 2 times S plus 4. So you can see that there are 3 poles and there is no 0 for this system. And GC of S is given as KP, or a proportional controller. So we want to draw the Root-Locus for this system and then compare it with what we get from MATLAB. We also have 2 points which we need to consider. We need to find the range of values of KP such that the closed loop system is biboy stable. And also we will see whether there is a value for KP such that the step response of the system using a second order approximation is undamped. Okay, so these are the things that we will consider later. But for now, let's focus on drawing the Root-Locus. So for L of S, we have GC times GP as usual, and then we will have 16 times KP over S times S plus 2 times S plus 4. And this could be written in the form of rho times 1 over S times S plus 2 times S plus 4, where rho is equal to 16 times KP. So we keep this in mind. And then if we look at the transfer function, we get these points. We have n equal to 3, because there are 3 poles for our open loop system. M is equal to 0. There are no zeros for our system. And R, which is equal to n minus m, will be also equal to 3. And this means that there will be 3 asymptotes, for which we need to find out later XA and CA, the point of abscissa and the angles of the asymptotes. Let's start by preparing the S-plane for each one of the positive locus and negative locus. We have the real and imaginary axis. As usual, we start to determine the location of the open loop poles and zeros of the system. If we consider L in the form of n over d, rho times n over d, setting d equal to 0, we will get the open loop poles of the system. We will have S1 at the origin, S2 at -2, and S3 at -4. And there are no zeros for the system, therefore we will have 3 poles at the origin, at -2, and at -4. So we do it for both negative locus and positive locus. Then we can start to find out the point of abscissa and the angle of the asymptotes and draw the asymptotes later. XA is in the form of sum of zi's minus sum of pi's over n minus m. There are no zeros, so XA will be equal to 0 minus, for the poles we have 0 plus 2 plus 4 over n minus m, which is 3 minus 0. So we will get -6 over 3 or -2. -2 will be the point of abscissa. XA is equal to -2. Then we need to find out the angles of the asymptotes. R times CA will be equal to 2h plus 1 times pi and 2h times pi for positive locus and negative locus. And we need to set h equal to 0, 1, and 2 because there are 3 asymptotes. Therefore, we will have R is equal to 3. 3 times CA will be equal to, if we set h to 0, we will have pi, 3 pi, 5 pi for positive locus, 0, 2 pi, 4 pi for the negative locus. And then we will have CA equal to pi over 3, pi, and 5 pi over 3 for the positive locus, 0, 2 pi over 3, and 4 pi over 3 for the negative locus. Now that we have the angles and a point of abscissa, which is -2, as we already have found, we can draw the asymptotes. There will be 3 asymptotes. Starting from this point, for the positive locus, we have the angles equal to pi over 3, and 5 pi over 3. So this will be one asymptote with the angle of pi. This will be the second or the other asymptote with the angle of pi over 3. I hope it is kind of pi over 3. And then this will be the next asymptote with the angle of 5 pi over 3. For the negative locus, we'll have one asymptote with the angle of 0, which is over here. Then another one with the angle of 2 pi over 3. And the next one with the angle of 4 pi over 3. So what you see in orange are the asymptotes. We have the asymptotes for both of the positive locus and negative locus. As the next step, we can have a look at the part of the real axis which belongs to each one of them. Referring to the location of the poles and zeros that we have, we can divide the real axis into segments from -infinity to -4, from -4 till -2, from -2 till the origin, and from origin till +infinity. And then for each one of them, we can count the number of the poles and zeros for each segment. For the segment from -infinity till -4, you can see that there are 3 poles on the right side. So we have the number as 3. Then for the segment between -4 and -2, we have 2 poles. For the segment between -2 and the origin, we have 1 pole. And for the segment from the origin till +infinity, there are no poles or zeros on the right hand side. So we have 0. And by looking at the numbers, we can say that the first one belongs to positive locus, the third one belongs to the positive locus, the second and third segment belong to our negative locus. Let me highlight them in our plot. So from -infinity to -4 belongs to our positive locus, and also from -2 till the origin. On the other hand, for the negative locus, we have it from -4 till -2, and from the origin till +infinity. So these are our, indeed, parts of the real axis that belong to the root locus. And again, we know that the branches will originate from the poles, open loop poles of the system, and all of them will go towards infinity with the help of the asymptotes. Okay, so if we focus on the positive locus, we can see that there will be a branch originating from the pole at -4, and it will move on the real axis towards -infinity using the asymptote that we have drawn. So they will be one branch like this. For this pole, we don't need to find out the angle of departure, as it is obvious, and it will be equal to pi. For the branches originating from the pole at the -2 and at the origin, we know that they will move towards each other. They will meet at some point, and then they will depart the real axis. They will meet at some point, and we need to find out that point, and that point will be a breakaway point. So we need to find out one breakaway point for the positive locus. For the negative locus, one branch will originate from the pole at the origin. It will go towards plus infinity on the real axis using the asymptote that we have drawn. And then the other two branches will start from the pole at -2 and the pole at -4. They will move towards each other. At some point they will meet and then they will depart the real axis, and we need to find out that point. So that's also a breakaway point. And obviously for this example there are no break-in points because the branches never come back, let's say, to the real axis. So next step would be finding out the breakaway point. To find out the breakaway point, we need to refer to m prime times d minus n times d prime equal to 0. For n of s we have 1, which means that n prime of s will be equal to 0. For d of s we have s times s plus 2 times s plus 4, which is equal to s to the power of 3 plus 6s squared plus 8s, and d prime of s will be equal to 3s squared plus 12s plus 8. Then we can plug these values into the equation that we have. M prime times d will result in 0 times d minus n is equal to 1 times d prime, which is 3s squared plus 12s plus 8 equal to 0. If you find out the roots of this equation, we will get the exact location for the breakaway points. One of the breakaway points will belong to the positive locus and the other one will belong to the negative locus. The exact values S1 and S2 are minus 3.1547 and minus 0.8453. We can see that the S1, the first one that we have here, which is equal to minus 3.15, and it could be somewhere around here, belongs to the negative locus. So this belongs to the negative locus, and the other one belongs to the positive locus, which is at minus 0.84, and it's somewhere around here. Alright, so if we come back to our drawing our root locus, the two branches will meet at this point, which is at minus 0.8453, and then they will depart the real axis. The angle of departure from the real axis will be equal to 90 degrees, pi over 2 and 3 pi over 2, and then they will move towards the infinity using these two asymptotes. The next point would be finding out the intersection point with the imaginary axis. We will have a look at that later. For the negative locus, the branches will meet at the breakaway point, which is at minus 3.1547. They will depart the real axis with the angle of pi over 2 and 3 pi over 2, and then they will move towards infinity using these two asymptotes. Well, we are kind of done in terms of drawing the root locus. Let's have a look at the explanation that we have for the example. We need to find the range of values of Kp in R such that the closed loop system is bistable, and then we will see whether we can have the system approximated as an underdamped system. These are kind of related to each other, but let's have a look. So if we look at the negative locus, you can see that for any value of Kp or rho is smaller than 0, there will be one pole on the right half plane. So for rho is smaller than 0, the system will not be stable. System will be unstable. For the positive locus, for some values of row, the system will be stable. So you can see that let's assume that we have a pole originating, a closed loop pole originating from the pole at -2. It will move this way, this way, this way, and then it will move upwards. And at some point, at this point, the branch will cross the imaginary axis and it will move towards the right half plane, and therefore our closed loop system will become unstable. So finding out that point is quite important. And in terms of the stability, we need to find out what value of rho or Kp we have at this point. We know that it belongs to our Root-Locus, and we are also interested in finding out the actual value of S. Okay, we need to see where on the imaginary axis our branch crosses the imaginary axis, and our system is on the borderline of stability. Just before that the system is stable, and after that the system becomes unstable. One way to find out that value is to assume that S will have some let's say pure imaginary value. S will be equal to j omega, and then we plug the value of j omega into our system, S equal to j omega, and after that we just set in our equation we set the real part and imaginary part being equal to 0. The other approach would be to use the Ross-Horowitz criterion. If we form a table, we have S3, S2, S1, S0. If we form the table, keeping in mind that we have the effect of rho, let me maybe write it over here. So we have indeed 1 plus rho n over d equal to 0. We can rewrite this in the form of d plus rho times n equal to 0. For our example, we will have s to the power of 3. We have d somewhere, it's here. Plus 6s squared plus 8s plus rho times n, which is 1. So rho equal to 0. And then we can fill the Ross-Horowitz table. 1, 8, 6 rho, and then we will have minus determinant of 1, 6, 8 rho. Let me just find out the exact value over here. 1, 8, 6 rho. Rho minus 48, and this is equal to 6 minus rho over 8. So we will have 6 minus rho over 8, and over here we will have rho. So if you want to have our system stable, we would need to have rho bigger than 0 and 6 minus rho over 8 bigger than 0. 6 minus rho over 8 bigger than 0 means that rho over 8 should be smaller than 6, or rho should be smaller than 48. So rho bigger than 0 and rho smaller than 68 means that rho will be between 648 and 0, and this will be the range in which our system becomes stable. On the other hand, it means that over here rho is equal to 48. Okay, so we have found the value for the rho. It's equal to 48. Now we are interested in finding out the value of S. We can plug the value of rho over here. Out of this we will get s to the power of 3 plus 6s squared plus 8s plus 48 equal to 0. And for s we have s equal to j omega. So we will have j omega to the power of 3 plus 6 times j omega squared plus 8 times j omega plus 48 equal to 0. J omega to the power of 3 and 8 times j omega will have imaginary parts, and 6 times j omega squared plus 48 will have pure, let's say, real values. 6 times j omega squared is equal to minus 6 omega squared plus 48 equal to 0. So we'll have 48 equal to 6 times omega squared. This is 8, so omega will be equal to square root of 8, or 2 times square root of 2. And that means that we have the value on the imaginary axis where the crossing happens is equal to 2 square root of 2 and minus 2 square root of 2, because we have it symmetric with respect to the real axis. So we have found the range of values of Kp. We have found it for rho. Rho is between 0 and 48. But since we know the relation between rho and Kp, we can convert it to that. Yeah, Kp is equal to rho over 16. So this means that Kp is between 0 and 48 over 16, which is 3 over 2. So that's the range of values of Kp for which the system is stable. And then coming back to this point, we want to compute the value of Kp. Again, we have found the value of rho, which is rho is equal to 48, and Kp obviously will be 48 over 16, such that so this is 3 over 1 indeed, yeah? Such that the step response of the closed-loop system is undamped. So the system becomes undamped when there are 2 poles on the imaginary axis. For this case, in the case of positive locus, we see that it could happen. For k equal to rho equal to 48, we will have 2 poles over here, and there will be another pole somewhere like this. We can find the exact location of that pole, of course, as well. But that's not the question for this example. So it means that we already have found the value of rho, 48, and Kp is equal to 3 in that case, for which the system behaves like an undamped second order system. Alright, so I think that's all for this example and for this video. Thank you for watching, and see you in the next video.